Hello and welcome to our presentation about students' perceptions of computation after they complete upper level coursework. We are excited to get to share these interview results with you. We're going to start with some anecdotal stories about how students don't often realize that computation is an integral part of physics. We'll take a minute to talk about the framework we use to formulate this interview study, about how students form mental models of the physics community, and then we'll go into the interviews we conducted with 5 physics majors who completed upper level courses that involve computation. And we wanted to look at how does computation fit into their mental models after they complete a computationally integrated physics course. And we'll conclude with an overview of some recommendations we developed as a result of these interviews. So if you're here in an AAPT meeting, you've no doubt heard about computation and how important it is for preparing students for 21st century STEM careers. However, when we do introduce computation into our physics courses, students sometimes seem confused. They say things like, this isn't a computer science class. Should I take an intro to programming? But I'm not a computer person. Or, as I often hear, Dr. Lane thinks programming is important, but I don't know about everybody else. And so this leads to concerns, not just for us, but for many folks who incorporate computation into their courses. We're worried about the loss of student engagement if they think that this is just a hoop to jump through. We have to spend a lot of time in class generating student buy-in. And most importantly, what happens when these students graduate and go into industry and their boss expects them to know some programming that they weren't really paying attention to? So we formulated a research question: how does a computationally integrated physics course help to bring students' perceptions more into alignment with the reality of the discipline? In order to set up our interview study, we adopted a framework based on communities of practice and mental models. Communities of practice is the notion that a novice in a field navigates their place within the professional culture by familiarizing themselves with the community's common goals and the conventional approaches to attaining those goals. In the mental models framework, we study how learners use internal representations to guide their reasoning and form expectations based on their experiences. And we want to suggest in this framework that an important factor in students' pursuit of a field like physics is the mental model that they form of the community of practice that they are navigating. So, for example, one way we might represent the physics community of practice is with a pie chart that's got roughly equal wedges labeled experiment, theory, and computation to represent the type of practices that most physicists implement in their work. We would say that this is representative of the reality that we encounter in the physics community. However, we also see that students don't always seem to understand or perceive that computation is such an important part of physics. So whereas the reality has wedges of roughly equal proportion, the student's mental model of the physics community might look something more like the pie chart in the upper right, where experiment and theory take up nearly 50% each. And there might be a thin sliver where computation fits in for some people, right? So in order to explore these mental models, we interviewed physics students who recently completed a course involving computation. So in the fall 2020 semester at the University of North Florida, the physics department offered 3 computationally integrated upper-level physics courses without any prior computation in the curriculum. These were, for a lot of students, the first time they saw computation, although a few students had taken Programming 1 in the Computing Sciences department. All 3 instructors utilized Jupyter notebooks with Python and provided minimally working programs. So the students had very similar experiences in these courses, and a few of the students we interviewed even took more than one of these courses, such that the computational experience was reinforced. We interviewed these students in spring 2021 because we wanted to study how computation fit into their perceptions now after it was no longer required in their coursework. We wanted to explore questions like, do they see computation as a normal part of physics practice? Do they see computation as valuable? Do they see it as accessible, as a thing that they can even do? So here are the highlights of these interviews that we conducted. We were very encouraged to see that it is possible for students to develop at least some realistic expectations about computation. Specifically, every one of these students that we interviewed seemed to see computation as part of the standard physics practice. Their model is at least a little bit more accurate than we encounter anecdotally more at the introductory level. These students also see a variety of purposes for computation. We'll talk more about that in a minute. On the other hand, we do see some areas for improvement. These students struggle with their self-efficacy with computation, and in particular, they worry about their lack of experience with programming. So in terms of the purposes that these students see for computation, we saw several themes arise repeatedly. Students appreciate the visualization that computation offers, the efficiency that they get to make use of, the analysis techniques that they learned in these computational assignments, and computation's ability to facilitate sense-making and motivation. We really get the sense that the students saw computation as integral to their learning and also to their future practice as physicists. There were a couple of students who specifically mentioned expecting to use computation for personal purposes as an extension of what they had learned in their course. This is especially important because while we have professional authenticity in these courses, we didn't necessarily stress the personal authenticity to the students, so we're glad to see that that came up for at least a few of the students. We also see some areas for improvement. For example, students felt that they did not have enough time dedicated to practicing computation in order to develop their self-efficacy. One student pointed out that they were worried about how it took them until the last week of the semester to really be comfortable with programming. We mentioned earlier that some of these students had taken introductory programming, and they actually had a difficult time switching programming languages coming from JavaScript or C into Python, which they felt was a bit too loosey-goosey to match up with those other programming languages. This is especially important to many of us in the computational physics education community because we often tout this notion that learning a second programming language is fairly straightforward, and we may want to actually look into that claim. And finally, a few students reference concerns about their ability to retain their computational knowledge if they weren't keeping up with it each semester. So based on these interviews, we have formulated several recommendations for our department and the physics education community at large. We would like to see computation involved in more upper-level courses, that students should see computation at least once each semester. We think that instructors should spend a little more time explicitly emphasizing the benefits and purposes of computation. And we are currently working on developing a common set of computation orientation materials supported by the Pickup Group for Python and some other programming languages so that students can have a consistent introduction to these new languages. We would also in future work like to attend to this issue of student self-efficacy by emphasizing the collaborative and iterative aspects of computational thinking, that the students don't have to do this all on their own. We would also like to study students' needs when they are first learning programming and how we can better attend to those. And finally, we'd like to identify the resources that students activate when they're first learning computation. So that wraps up our presentation about students' perceptions of computation. Please have a look at our follow-up presentation about specifically how the instructors' perceptions of computation impacted their students' perceptions. Thank you all so much for watching. We look forward to talking with you.